quick recap. In the last video, on this exact cube, we derived the law of mass conservation, the continuity equation. Today we keep the same cube and the same recipe, but ask a new question. What makes the fluid speed up, slow down, push? That is momentum, and it brings in Newton's second law with forces, pressure, friction, and gravity. Here's the plan. On the very same cube, we derive the equation for momentum, the famous Navier-Stokes equation, straight from Newton's second law, step by step. Track the momentum, add up the forces, divide by the volume. First, the momentum inside the cube. Momentum is mass times velocity, so per unit volume, it's just the density times the velocity. Multiply by the cube's volume, and that's the momentum sitting in the box. How fast it changes in time is what Newton's law will pin down. Newton's second law says force equals mass times acceleration, the same as saying the rate of change of momentum equals the total force. For our cube, the momentum inside changes for two reasons: momentum carried in and out by the flow, plus the forces pushing on the box. That forces term is the new ingredient. Mass had nothing like it. First, the flow carries its own momentum across the faces, exactly as it carried mass. But now the cargo is the momentum itself. We label the left face's position x, and the right face, one box width further along, x plus delta x. The difference in momentum flow between those faces, and because the cube is infinitely small, becomes the term on screen. How fast momentum is spreading out from the point. Now the forces, starting with pressure. Pressure pushes inward on every face. The pressure on the left face pushes the box right. The pressure on the right face pushes it left. If it's higher on the left than the right, the box gets pushed right. And because the cube is infinitely small, that net push becomes minus the gradient of pressure times the volume. The second force is friction, viscosity, picture layers of fluid sliding past each other. The faster a layer slides relative to its neighbor, the harder they rub. Newton's law of viscosity makes that precise. The friction per unit area grows in step with how quickly the velocity changes from one layer to the next, and the viscosity, the mu on screen, is simply how strongly the fluid resists that sliding. Put that friction on the cube's top and bottom faces, dragged one way by the fluid above, the other way by the fluid below. Their difference, with the cube infinitely small, is how fast the friction changes across it. And because the friction follows the velocity slope, that change measures the velocity's curvature, how much the flow bends from layer to layer. Do the same on all three pairs of faces, and they add up to the total bending of the velocity in every direction. The term on screen, that's the friction force on our cube per unit volume. The last force is the simplest. Gravity is a body force. It pulls on all the mass in the box at once, acting through the center. Density times g times the volume. Now put it together. The rate of change of momentum plus the momentum carried by the flow equals the three forces: pressure, friction, gravity. Divide every term by the volume and there it is, the Navier-Stokes momentum equation. It looks heavy, but it's just the 5 pieces we built one at a time. Here's what it's saying. It's Newton's law. The left side is mass times acceleration, how the fluid speeds up, including being carried along by itself. The right side is the forces, the pressure gradient, viscous friction, and gravity. For an incompressible fluid, that's the form you'll see again and again. So, momentum. The same cube, but now we tracked momentum instead of mass and added Newton's forces, pressure, friction, gravity. Per volume, that is the Navier-Stokes equation. Mass and momentum together are the beating heart of CFD. And in the next video, we do the same for energy. See you in the next one.